Hello, everyone. Can you hear me well? Thank you. So as usual, today we will start with a quiz that will start at 11:10. So any questions before we start the quiz? And after you're done with the quiz at 11:25, we'll continue with the regular tutorial where I'll show you a couple of examples of different problems with assembly. So we practice a little bit, give you some home exercises to practice as well. Okay. So if there are no questions, then I'll be here, and you should expect for the quiz being available as normal at 11:10. We'll wait a few more minutes for some people to finish, and then we'll start. Okay, so guys, can you hear us? Can you hear me? Okay, so let's start. I guess there was a question. I understand that some people don't had enough time for the quiz. I guess next time we're not going to reduce the time for the, increase the time for the quiz, we'll probably reduce the number of questions. One thing I want to highlight that there are certain questions that you guys are not doing well on previous quizzes. So those topics we keep reiterate. We keep asking similar questions again and again on caches. So if for several quizzes you cannot figure those out, you should, ask TAs, ask on Piazza, ask me in one-on-one. So you should figure it out, right? It's important. So this is why some questions, and if you practice them and figure out from previous quiz, they shouldn't be a challenge for you and should prepare you for the exam. Okay, so let's go back to the tutorial. As usual, I would love to see at least some faces. So if you can turn on your camera, please do so. That's really helpful to see whether I'm going too fast or too slow, especially when we ask for assembly questions and I need to see whether people are actually working on it or you're just waiting for the answer. Okay, so please, if you can turn on your camera, do so. Okay, so today, no surprise, we're going to talk about assembly. And essentially, we're going to do several different questions. I will leave you some questions to do at home. So here is one problem. We're going to go into a lot of details and we'll show how we address challenging questions that are written in somewhat of a plain English text, how we approach them and set them up and write in assembly, which is not the easiest language to program for sure, but it's still doable and you can do like decent code in it. So the question here is, how do you write an assembly language program that performs essentially multiplications of two registers, T1 and T2, and plays the results in T0 without using mult or mult unsigned instructions? So essentially, you need to run multiplication manually, right? So those questions are much easier to solve if you break them into pieces. And Terry already wrote loop addition. Yes, we're going to use loop addition for sure. So we're not going to do anything more sophisticated here. But how we're going to want to prepare all the code so that things work out. Because if you try to write it from scratch, it can break in many pieces. So, you want to use a classical divide and conquer approach. You want to break the problem into small pieces. Yes, you need the idea. Idea is a loop addition, right? So the first questions here is, how can multiplication be done using add? And we already get an answer for that. Multiplication can be done by adding multiple times. right? So, well, someone proposed powers and other things. So we want you to do a loop here, not to find an extra, instruction that can do multiplication for you. So there might be something other than multiplication you can use, but that's, also error prone. So yeah, let's not go into that. So essentially, let's do it properly through a loop. So first question is, algorithm, we are clear about it, right? We can do addition. So the question is, there can be corner cases. So first of all, what if one of the variables stores a 0 value, right? So you don't want to enter the loop if there is a 0 value. So then the questions you want to ask, how do you make a loop happen? So you need to write a loop. How do you stop the loop, right? So you first write a piece that loops forever, and then you find, and then you add a branch outside of the loop, right? And then there is such a theme that you're going to learn in other courses, like compiler related, called pre-loop or pre-header. So what do we need to do before the loop starts? That's usually preparing all the variables to be set to the proper conditions before the loop starts in the proper registers. Okay, let's do it. Any questions? So this is how you approach the problem. Like when you're given a relatively complicated stuff to do, like when, for example, when I was an undergrad many years ago, we were given a problems like a quick sort implementation or bubble sort implementation in assembly. And I think I mentioned that we wrote some tiny viruses as well that infected like executable files on old Windows machines. So this is a type of task you can still do. And those things you cannot solve in assembly if you don't have a proper approach that breaks down things in different pieces, right? And you also need to be very strict in how you would write code with assembly. So you respect certain, certain usage of registers. You want to know that how each routine or how each loop changes certain registers. So you don't get one piece of code of your own break some assumptions of the other code, right? Because there's no here like such things as local variables, like everything is visible globally. That's one of the downside of assembly programming. So you can easily break someone else's code by writing into some register. Okay, so in general, that's more like a note for a regular exam. So you can always assume you don't need to memorize instructions. So the instructions, symbol tables, and all these, things, like a cheat sheet that's given for you in the exam. So you can always use it, whether it's in-person exam or, virtual exam. So you can use that. So the math. So how can multiplication be done using that? That's the first question. Someone asked, do we assume T1 and T2 are positive integers? So we would probably need to check them. So essentially, in the ideal scenario, if you would use the right user code, depending on the type, you might do some assumptions. So for example, there are no such things in C. For example, you would have unsigned and signed types, right? And you can just make something unsigned type. So that's your assumption that it's positive or not negative, right? In assembly, it's all about interpretation. You're given a number. So if the number is coming from the user and the user can input you a negative number, you need to be aware that you might need to either output an error or things like that. We're not going to handle this right now, right? We assume that the user knows what they're doing and they enter the correct numbers, right? Positive numbers. But in general, it's a very good question. There can be always those errors, right? So we assume here it's non-negative, right? The user has no way to enter the negative number, and we can interpret them as non-negative, but there can be still zeros, right? So if we want to use this idea, we want to add T0 many times. The problem is, what if T0 stores a 0 value? So we need essentially a branch, right? That would check T2. And if T2 is 0, then we just jump to an AND and we bypass all the multiplication code. So this is how we start to build our code piece by piece, right? So how do you make the loop happen? Well, the loop should start, right? And there should be a jump back to the start, right? So you need to have at least one label that starts the loop. You can call it start, you can loop, call that loop or something, and there should be unconditional jump to that start. Then how do you make to stop the loop, right? At the start, we have these conditions on T2, and then we would make sure that at the end of the loop body, we decrement the register T2. That is one of the parameters. So as we decrement T2, eventually we're gonna, no matter how large it is, eventually it's gonna come to 0, right? And then if that happens, then it means that that condition would be actually true, and we will jump to an end. Is this part clear to everyone? So any questions so far? So you see the beauty of this approach. So someone said no. The hand is this. Do you have a question? Okay. Yeah, so essentially you see, if you approach the problem this way, that every single step I do is very simple, right? So there's no like really complicated things here. So we're almost there. So we just need to answer what needs to be done at the beginning. So at the beginning, we need to add T0 with just 0, right? Value. We need to set the accumulator. We're going to store the results to 0, right? Because that's where essentially we're gonna store the final results gradually. And here what we get, so essentially I am omitting this, any extra conditions if you would want to verify them non-negative, but that's essentially it. So we set up, that's, as I said, that's typically called pre-head or pre-loop, the things you execute before the body of the loop to set the variables to the proper conditions. Here we assume that T1 and T2 has the right parameters at the beginning. We just need to check whether T2 is not 0 because we repeat things that many times, right? One question to you. We are checking that T2 is not 0. Why I don't check that T1 is not 0? And after someone answer that question, I'll come part to your question. So about why didn't we store T2 in another register in case we need it later? So part that we are subtracting from T2 each time. Yes, that's true. We are subtracting from T2 each time. So if T2 would be 0, we are being in trouble. But why T1 is not a problem? It's in general. And do I do it efficiently or not? Like I took this code from previous instructors, and it is as simple as it can be, but it can be done better. Yeah, so Kevin Fernandez said that's correct. So adding 0 to itself still results in 0, but imagine, and it's correct. So so we add a loop. So imagine there can be a situation that T2 is 1 million and T1 is 0. So we're going to do 1 million iterations of the loop, just adding zeros, right? So it's going to be a correct output, but it's very wasteful. So if I would write this code, I would add another branch. So before even add T0 to 0, I would add another branch that checking that. So essentially, I would add T0 to, so I have the same line, add T000 to set up T0, and then I check another branch equal for T1 for 0. And if it's 0, then we're done and we can just jump, right? So there's no need to do the loop. Like the 0 is already an answer if one of their outputs is 0. Okay, so this is something that an extra line of assembly can save us on performance. The solution is though correct, but performance-wise, it was not very good, right? Okay, is this clear to everyone? So how that can be improved, but it's still a correct solution. It's not very optimal. Okay, so that's pretty much it. So that's how you can take a real problem and quickly convert it into an assembly code. And if you just stare at it without the comments, it's not particularly clear what's going on. So always comment your code well. And now going back to parse question, shouldn't we store T2 in another register in the case we need it later? Anyone wants to answer these questions before I do in the chat? So why I'm not storing T1 and T2 and manipulating them and not preserving them? So George said we don't need it later. Well, it's partially true, but how do we know that it's okay to play with it? This is not written in the rules, this is conventions. Not about division. Anyway, so the registers T stands for temporaries. So there are permanent registers and saved registers that people like to preserve, right? Oh yeah, Kevin said they are temporary registers. Yes, so that's essentially the answer to this question. So those registers are meant to be temporaries because if I want to write any code, I always need to multiply some registers. I cannot always save all registers because they can be changed. So that's why I'm given a set of T registers, right? And those registers are temporary. I can essentially under normal conditions, your functions shouldn't assume that those registers has to be preserved. So no one can rely on those registers being like particular values. So if you want to use these registers, you can as temporaries. Don't assume that they preserve across someone else's code. If you want to set them up, you always set them to zeros or any values you want, right? But anything else you can assume. So in general, this is all conventions. You can use it in whatever crazy way you want. Assembly doesn't limit you in any way. At the end of the day, it's all machine code, and machine doesn't care about what you semantically mean, but each particular register, right? Okay, so we're done with this question. As a part of your homework, I gave you an example from one of the older exams where you would need to write a short assembly code for a function like that with if statements, which were practiced several times, different if conditions before and returns. So please practice this at home and use the same strategy, right? So build it piece by piece. Don't try to write it all from scratch. Do it piece by piece, right? That's a good, it's a relatively small piece of assembly code, right? But there are still places to make mistakes. Okay, so let's now in the time, any questions, by the way, about the previous problem? Did you get, I try to go very, very slowly through the question one so you can see how those solve. And now we practice a few things a little bit faster. Any questions? Okay, if there's no questions, let's try this problem. It's relatively simple. I just want to make sure you guys don't feel asleep. So translate the C style code into 4 lines of MIPS assembly code. So I want, I'll give you a few minutes, right? Please try it out and type the answer in the chat. And guys, please do actually try. That's the whole point of the tutorial. So I know someone is going to type the right answer eventually, but the whole point here is to try it out. And if it doesn't work for you, you would get a question, right? And that question I can answer. But if you don't try, I don't get a questions, I have no chance to teach you. So the naming of the C-style code is intentionally using T1, T2, T3 to simplify you assigning registers and things like that. Okay. We already have someone wrote the code. So I think I'll wait a little bit more for other people to try before showing the solution. Yeah, as you can see, there are multiple ways to achieve the same goal, right? So you can use, loads, or you can use adds, right? That's semantically equivalent. And yeah, I think And you can see like someone did a shift similarly to me, and someone did an add of two same registers. You can do the same. It's usually considered that shift is a little bit faster, although I had to be honest, in most architectures it's not anymore. Usually the shift is faster in terms of circuit implementation, but yeah. Okay, there's another solution. Yeah, there are different variations, but you can see that everything I see so far, there might be some little typos here and there, but they are usually correct. So I hope you guys got it, right? That was a simple example of the code with just assignments and multiplications. Okay, let's do something a little bit more complicated than that. And that's the last problem for today. So let's deal with this. This is an array, right? And I referenced the array twice, right? You can assume that variable I, say, at the top of your stack, like in register GP. So Parth is asking for the previous questions, why you did shift? Well, multiplying by 2 is the same as shifting by 1. Left. I think we did this trick many times before. So multiplications by powers of 2, 2, 4, 6, and divisions by powers of 2 is usually done with shifts. But in the case of 2, addition is almost as efficient as shift. So there's not a big difference. But anything more than that, like 4, 8, you would definitely want to do a shift. For people like me who learn, who work with older machines, where sometimes those are different between shift and add, I'm so used to it, so I naturally use shift everywhere. But I had to admit that for certain codes right now, that's not such a big difference. Yeah, there used to be in the older machines that multiplication divisions would take tens of cycles and they were very slow. Now things are not like that anymore. Okay, I hope everyone understands what you're doing, right? And you got familiar with loops, right? I show you pieces of loop codes before. Here you don't need to write the data code. You can assume you had array properly allocated in the data segment. So you just write the code to access it. Remember, I showed you some pieces with loops before, like 2 lectures ago, and I think you've seen some code with Mustafa as well with loops, so it shouldn't be a surprise for you. So I've given you maybe another minute, but please try. I know like sometimes it feels boring because that's assembly, but it's a very good practice because if you don't try it yourself, like, to be honest, you're not going to probably in your life write a lot of assembly code. But if you're going to do any engineering or system level development or research, you would have to look at the code. Why? Because sometimes your code is going to be generated and you don't like the performance. And if you don't understand what's going to with it, you would actually have to look at assembly, what was generated, because you don't know whom to blame. Is that you? If it's algorithm, then it's you. But if it's not algorithm, if the algorithmic everything is fine, but it's still slow, you want to see what the compiler generates. Then you would open the assembly code. And if you never try to write it, you're going to be like, oh my God, what's that? Like what this thing is doing, what this branch means. It doesn't have no intuition for you. Because remember, compiler is not human. It's not going to generate you comments in the code. It's not going to explain you what it's doing. So it's like playing chess, right? If you can read, if you play chess, you can see by people doing the moves, what their strategy is, what their intent is. But if you never played it, you look at their moves, all moves look like somewhat random, right? It's the same here. You would need to write your own assembly at least a little bit so you can understand the generated code that you have to deal with. So most people don't write assembly anymore themselves, but compilers still generate it, and that's really the language that computer speaks. Okay, I'm waiting for the first answer from someone. And even if you get a partial results, please type in. remember, there's nothing super complicated here, right? It's like compilation process for a single statement, like single instructions, relatively straightforward. There's no like black magic here. So compiler can do very sophisticated optimizations across many instructions and loops. And if you take more advanced courses in 3rd and 4th year, you might learn about that. But right now, we're just literally translating line by line. We're not doing any fancy optimizations here. Okay. Can at least someone tell me that they're working on it so I know that I had to wait versus like nobody is doing it and they're just waiting for the correct answer. So is anyone still trying to get it right? Okay. Okay, seems like at least someone is trying. I see both yes and no, so I'll wait a little bit, a few more seconds. If you want to show your partial work, not complete, but at least partial for some of the statements, you can send it as well in the chat, so you can compare them with my notes. And don't afraid to be wrong. You're not judged here. You're here to practice. So the key thing, okay, I guess I'll show it because I still want to go with the example so everyone. Oh, really? More than 7 minutes? Okay, let me show you the code. And it might look like, but remember that a lot of here is comments. So this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of code, right? So let me explain, and some of these are very trivial. So I'll go with it, over it. First of all, we prepare everything. And there can be different conventions. Here, assume that variable I is pointed by this register, so loaded, but you can just assume sometimes you have it. That's not a big deal. So you had register I, value I in register T0. And then you need to fetch address, you need to fetch array in register T8, so know where the array starts, right? So what do you do next? Well, I want to get I divide by 2, and then essentially what I did here, and I did a few optimizations here to confuse you a little bit. I'll show you why. So compiler would do it slightly differently, but as a human, I can optimize on the fly. So I'll show you some tricks. So I did this division. So shift right by 1, right? Which means I divided by 2. That should be easy. I get this part. So then remember that these indices here in our MIPS, all arrays are 4-byte values, right? So this index, even though it can be 0, 1, 2, 3, 4, it jumps in the increment of 4 because each value is 4-byte in the array, right? It means that to iterate, to get the offset of the right piece of memory, I need to jump by this index multiplied by 4. So to do that, I take my index I plus 2 and convert it into a 4-byte offset. I multiply it by 4. And then I generate this address, right? And as you can see, this is just I plus 2. And I didn't do this plus 1 here. Why did I do? Because I know that the load instruction here that has a special offset plus 4. So I could have used an extra instruction and add 1 here. So that would be 1 line longer. But I know there is a constant 4 here I can place in, right? Or any constant that I like to the load. So instead of having 1, and that is 1 would be shifted by 2, so it becomes plus 4 really. Instead of avoiding all of that, I really put this constant in here. But just to clarify here, so I got first the offset in the array, then I get the address of that array, right, by adding the beginning of the array that was stored in register T8 and I added the offset T1 I computed here. So this is get me this element of the array. And then I fetched the array stored in T1 plus 4. That's how you read this thing. Right? This plus 4 is for the offset. You could have done differently. You could have 0 here, then you would need another plus 4 here. But I try to save one line of code, right, for this constant. So this is how you fetch a plus 1. Then the result of that is stored in register T1 because I don't need it anymore. And then I could essentially add this thing here, right? So I add this variable plus 1. That's straightforward. Then I need to store the results into AI. So that's relatively straightforward because the index is just I. So you take T8, and right, there's no offset. You would just need to use essentially the register, and then that's pretty much it, right? So it should be T2 here, okay? So you just get address of AI, right, by adding the offset. Sorry for the typo, it should be T2 here. And then you store the result reading from this address. Okay, this is the parameter you store, and this is the address. Any questions on how I did it? So you see how I break the problems into. So I said there is one array access, another array access, right? Both of them need the beginning of address A, so I stored in some register T8. And then I did this separately, and then this separately. And then I glue up the logic together. Whatever I get from here, I save into here, right? And the key thing to manipulate with registers, it's you always start with an index, right? You compute the index you need to access. Then you take this index and you need to shift it by 4 because it's an increment of 4, assuming it's your word is 4 byte, right? Yeah, good questions. Why you shift by 1 and then you shift left by 2? Well, because that's kind of like if I would collapse that, you would be definitely confused, right? Why would I shift something by just 1? So you're right, the compiler, when you're going to see this code, would merge that into one shift. But that's an optimization, right? I don't want to confuse it even further. So we first it shift to right because it's divide by 2, and then it's multiply by 4. But divide by 2 multiplied by 4 is equivalent to multiplying by 2, right? So you could have done just shift LL by 1. Sam is correct that it could get rid of, but that's an index, right? So you need to be careful on whether there is any, let me think. So it might actually, in some, it might depend on their, and the bits. So if you divide by 2, now actually in this case, I don't think it's going to cause a difference. If you would do it the other way around, you shift left and then right, then there might be differences. But here it's not, because what's going to happen is you just kill the last bit by shifting, right? And then you shift back. So no matter what, you would just, move the 0 bits here. So I don't think there's going to be a difference here. At least I don't see how. So the signed bit might be a problem, but I assume that this is like an unsigned integer here as an index variable. So the sign should be 0. Okay. Again, this is anyway an optimization that you cannot do under certain conditions. There are certain things that you can definitely do. But here I want to show you that a straightforward way. So this is I divide by 2, right? And that's to get this original index. And then you want to get to multiplication by 4 because it's step 4. Okay, any questions about the code? Sam, did I answer your question? Or I didn't convince you? So essentially, in a general case, right, you're right, you cannot just do it because there can be a sign bit here. But if you know that a compiler can prove, for example, when it generates the code, that this variable was an index and it's unsigned, very frequently it's a constant actually, or if not a constant, it's unsigned integer, right, that you use. Then you know that the sign doesn't affect anything, so you can safely shift. So the shifts are equivalent, essentially. If you do shift right and then shift left, it's not going to make any problem. So it cannot be done in an assembly itself, but it can be done when you see the C code, and when you generate it, you know it's equivalent. So the compiler would have to prove that transformation is safe. But again, I didn't do it here because I don't want to confuse it, and because it's not in general case correct. It's correct in some common cases. Okay, any other questions? Okay, this is pretty much what I have for today. Oh, someone has, I think they said several times it's a typo. It's supposed to be T2 here. So there is no like $2 here. It's supposed to be registered to. Okay. If there are no questions, then I'm happy to answer your questions. So if you want to meet with me one-on-one and talk about especially general questions, please send a message here and I'll bring you to the breakout room. For a tutorial, if you had questions, I hope you will get some questions because we try to make it a little bit more complicated this time for you. Please study them first, try to figure out it on your own. And if you don't find the adequate answer, you don't understand the question, then pause the question on Piazza and we'll get to it and answer your questions. But if you had something more general or something you didn't figure out or even was not ever answered in Piazza for a week or so, please stop by right now and I'll try to answer your questions. I try to make sure you understand. We're gonna keep if you guys are gonna perform, I'll look at the statistics. If you're gonna keep performing badly on caching questions, you're gonna keep getting them in quizzes until majority of you will get it, right? So I want to make sure you understand it. So you're not gonna be escape. And I'm definitely gonna bring these questions in the exam. So you'd better figure it out. You're not gonna escape. Yes. So I really want you to understand how indices work. So there was several answers to the previous questions on Piazza with the detailed answers. Yeah. So this is the question you perform badly, and I'm going to keep bringing it in until you learn it. Okay. Anyway, jokes aside, whoever wants to stay and ask questions one-on-one, please send a message here, right? If not, thanks everyone. And yep, good luck with your projects and have a nice weekend. Thank you, guys.